All right, so welcome to the second presentation for chapter 22. So this is our second part of the nuclear chemistry chapter and unit. So we're talking a little bit about nuclear fission and fusion in the previous chapter. We just kind of got started on that in the last lecture. So here we're continuing on, taking our quick look at that nuclear fission, where the nuclear reaction where things break apart. So to give us an example, of course, of the classic uranium-235 that fuels nuclear fusion bombs. It's struck with a neutron, fast-moving neutron, and then it splits apart into two smaller nuclei. And then it fuels and creates more neutrons, and that powers the chain reaction process that has been mentioned before in the vocabulary. So for nuclear fusion, then lighter things come together to fuse, and this is what powers stars. And typically we look at the fusion of hydrogen into helium because that's typically what powers a star. And you can see we also have electrons emitted in this process as well. But we don't need to have all these neutrons flying around. This process doesn't necessarily involve fast neutrons in every single instance, but it does require extremely high temperatures, extremely high pressures, and containment in order to keep this going, right? Because we're trying to push together positively charged nuclei in order to get them to fuse, because the electrons have all been stripped off at these high temperatures. They're basically just like a plasma. So we need to keep a lot of energy going in order to get this fusion process going and overcome the electrostatic repulsion. So that's why we need all this energy typically in fusion. If you've heard a little bit in the pop science about fusion, right? We need to have high temperatures, high pressures, and there was always people looking for some way around that, the so-called cold fusion way around that doesn't really exist. There's not a way to do that, but it's just something to keep in mind. What the difference between fusion and fission is. Fission is typically what we see in like the classical nuclear bombs. They can make fusion bombs too, but the way they generate the high temperatures and pressures for a fusion bomb is they actually set up a fission bomb first. I mean, that's how much energy it takes. So just kind of keep that in mind again with the scales. So again, they look here at the uranium-235 fission process. Again, that's the classic one, the first one that was used in the first fission bombs. And again, the chain reaction is sustained by the fast neutrons that keep going. And that's how, like when they run a nuclear reactor, which they also use uranium and other isotopes for fission in that process, other elements like plutonium and such can be used too. You'll use lead or other heavy element control rods that can suck up these and slow down these free neutrons so you can control the rate of the reaction. This is discussed a little bit later on in the section on different types of nuclear reactors, but since I don't test that and doesn't come up in the homework, I'm not going to go into a lot of detail there. I'm just giving you a little bit of context here. So the critical mass is having a sufficient amount of this uranium present in the system so that you can keep the neutron supply high enough to create a chain reaction. In early work and development, they had these nuclear piles that were very small. This is like in the 1930s. And again, they used control rods, and these systems would just produce heat because they'd keep them in a lead-lined box so they wouldn't be exposed to any of the high-energy gamma rays that come off this too. They don't mention those in the reaction, but there's a lot of high-energy gamma rays that come off there. It radiates. This is where you get the cancer from being close to these things. So just be very careful, of course, thinking about this. But you got to have a certain amount of this material. It's got to be sufficiently enriched, and it's got to be sufficiently clean in order to generate this flow of neutrons to keep a process going in fission. So again, they look at an example here of a fission process, and it works out similarly to the one that we looked at before when we were looking at binding energy per nucleon and putting something together, right? They look at the energy released in a nuclear process, a nuclear fission process, right? So they look at the mass of the uranium, they get the mass of the isotopes, they subtract the other masses, and they're calculating a mass defect in the same way. This mass change is the mass defect, that's delta M. And then it's weird to think about that there's a change in mass, but that's really what is going on here. So we calculate this as a change in mass. They convert it to a mass difference in grams per atom and plug it into the equation. You got to put it in kilograms. Again, remember, if you're going to use the Einstein equation, you come out with a number in joules, but that's again per atom. That's per atom. So 10 to the minus 11, we got to multiply that by Avogadro's number in order to scale it up, and they convert it into kilojoules. They do both here. And this is where you're getting this times 10 to the 10 kind of size scales, as well beyond any kind of chemical process, any kind of chemical explosive or anything releasing this much energy. So they say the nuclear fission of uranium-235 releases 1.0 0.68 by 10 to the 10 kilojoules per mole. Again, that's a better scale for something that's actually taking place, because when you're gathering together an amount that you could sit on a table, an amount that you could actually measure mole-sized amounts of uranium, you get an enormous amount of energy in that fission process. But you can see here how we calculate that and how we can use the Einstein equation to get a good sense of the scale here, and how, again, that scale is well beyond any kind of chemical process. So nuclear transmutation. So there'll be a number of these nuclear transmutation problems on the test, and also you'll see them in the homework. These are basically like chemical equations, like balanced chemical equations. And we're going to be having to fill in some gap or identify which kind of process it is as we're doing problems like these. These are probably going to be the most common problems that you'll see. These other ones that we've talked about are good for context, and we should have a good sense of how to calculate that. But this is sort of a new type of problem, right? These are sort of like balanced chemical equations, right? So here they talk about bombarding a nitrogen-14 nucleus with an alpha particle or a helium nucleus to form oxygen-17, and a hydrogen atom also comes off this. So this is like a balanced process, right? Because you could add up all the masses, you get 18 mass across on the left side, and you get 18 mass if you had 17 and 1 on the right side. And you get 9 mass if you had 7 and 2, and you get 8 and 1, and that gives you, so everything is balanced, right? So keep in mind, these balance in a similar way to a chemical process. So we'll look at some other examples here. So here we have uranium-238 isotope being bombarded with alpha particles or helium nucleus. And we can see how if we add 238 with 4, we're going to get a mass of 242, but we have this neutron over there, so we got 241 and a neutron. And if we add 92 and 2, we get 94. So we can see how this is balanced across, right? So when you're working out problems like this, you may have to identify which element it is using your periodic table to look up which element goes with the atomic number, the number of the element on the table, or the number of protons. Those are the same thing. And then we can look down here at some other examples. They mention one that's used in certain smoke detectors, americanium, and the transmutation of plutonium to that, and to neptunium. Again, if you add across the mass, you'll see that that adds up on both sides. And if you add across the number of protons or the atomic number, you'll see that that adds up. And where an electron is a -1, so 95 minus 1 is 94. Again, this is pretty straightforward, but remember that you have to keep everything in balance like that, similar to a chemical process. You're just looking at the mass and the charge, so those have to be correct across both sides too. And again, we look at some other examples, cobalt-60 and radiation therapy. You can also add together these processes just like you can a chemical reaction. So if you have multiple steps, you can combine them into one overall reaction, kind of like a Hess's law sort of thing, like you would have in a chemical process. And again, we're going to review these different processes, because some problems you'll see will have you classify a nuclear transmutation as a beta emission or a positron emission or an electron capture or an alpha emission. So you may want to go back to and see if your reactions fit one of these. Now, there'll be nuclear transmutations that don't fit any of these, but bear in mind that some of them will, and there may be questions that ask you to classify into one of these 4 categories. So again, just keep that in mind. Again, balancing a nuclear transmutation equation. Again, it's very similar to balancing a chemical equation, except we're looking at both the top and bottom numbers. So they say here that berkelium has a Z97, but how would we know that? I mean, if we were given a problem like this and they just said the element berkelium was prepared at the University of California at Berkeley at 1949 by alpha bombardment of americanium, they say 2 neutrons are produced in the reaction. What isotope results? Write a balanced equation. So you'd start with the americanium. They start with that, 241, 95 americanium. You add in your alpha particle, that's your helium. But if you don't know what berkelium is, you would have to check that on a periodic table where you could look up the 95 americanium and look up your 97 berkelium here on this slide. So make sure you have a periodic table with you to be able to do these problems. Remember that on all my exams, a periodic table is allowed, as well as a calculator. So you want to make sure that you're using this as the tool that you will need. So now that we know what berkelium is, that it's 97, we can write it down, and we can see that its mass is going to be minus the 2 neutrons. It's because if we had 241 plus 4, we'd get 245. We take away 2 mass for the 2 neutrons and get 243.97 per clinium. So this is a type of problem you might see in homework or on an exam that has you use the periodic table to figure things out. Again, don't memorize where elements are on the periodic table. Don't do any of that. Just use the periodic table as a tool that you need to use it as to be able to find names for things or see what the atomic number is so that you can fill out these kinds of questions. Okay, so here's another example where we've got argon plus a hydrogen nucleus, and we're going to release 1 neutron here. So we know that the mass overall is going to have to be 40 on the right side, okay? And we know that we will need to get 19 on the bottom so that the sums on both sides will work. So we know we got a mass of 40, and we know that it's number 19. But what element is number 19? How would I know that? Well, I'd go back to my periodic table, and I'd look for number 19, and that's potassium. So now I know that potassium is number 19, and I could get the answer as 4019K for potassium. The answer is not written here, but that's how you would approach a problem like this. And I just want that as an example to show you how to use the periodic table to look up things. So some further applications of nuclear chemistry, right? So there are a number of applications discussed in the text, but the most important for our purposes and the kinds of problems that you'll see in the homework and the test will be radioactive decay and carbon dating as a good example. Radioactive decay, like I said, is a first-order process, and so we're going to do a little review of that first-order process here. So carbon-14 is a radioactive isotope of carbon. It is created in the upper atmosphere as nitrogen from the atmosphere, just regular old atmospheric nitrogen, is bombarded by neutrons that are part of the solar wind that come off the sun, and they hit the upper atmosphere, and sometimes they turn into an isotope of carbon and a hydrogen in that process. Okay. And then this also will decay back via beta emission or the release of an electron. It'll turn back into the nitrogen. So this process is sustaining. The nitrogen comes back and it can get hit again, and the same thing this process can keep going. Now, since this process is a function of the upper atmosphere and how much nitrogen is there, that's relatively consistent because the atmosphere is mostly nitrogen. So the creation of carbon-14, that part is relatively consistent no matter what humans have done and no matter what is going on the planet. But what is important to consider is the carbon-12. Most carbon in the carbon cycle, which means, living things when they eat things, or even carbon that's even in rocks that's on the surface, it's almost all carbon-12. Carbon-14 is extremely rare. It's like less than 1% of all the carbon on Earth. They mention that as one part in 10 to the 12th power, so a very, very small amount. So keep in mind that there's not going to be a whole lot of this carbon-14, but if we built, you can think about it this way, if we built a really sensitive device that could detect these differences in mass, we might be able to see this. Now, if for some reason the amount of carbon-12 changed, what was bioavailable changed, like if a volcano went off, or if we, say, burned a lot of ancient carbon that's buried in the ground in the form of fossil fuels, there's no carbon-14 in any of the fossil fuels that we're burning because that's all old carbon that's been buried in the ground, any carbon-14, and that has long since decayed. So if we do things like that, that can change these ratios. Also, if we set off atomic bombs, which we've done, we can partially generate some of this carbon-14 ourselves. So this ratio is not perfectly consistent over time, but if we know sort of the historical context, we can get a view of, since the carbon-14 generation process in the upper atmosphere, that part's consistent. And if we go back in time far enough, if we're looking at something that's relatively old, it's before atomic bombs, it's before the mass combustion of fossil fuels, then we might be able to get a sense of how old it is based on how much carbon-12 there is to carbon-14. And this process is slow. It's got a half-life of like 5,700 years, about 6,000 years. And when a plant or animal dies, or let's say something that's derived from a plant or animal is made, so like animal skins or plant food materials that are ancient in origin, thousands of years old, we could use this to get a sense of how old that really is. As long as there's nothing that has, changed the carbon. Sometimes if certain artifacts are near a volcano or in a fire, or if things have happened to them that might change their carbon ratio or bring in new carbon, then that might mess this up. So this does have some error types that we're aware of, but in general, we can use this to get a sense, right? Because if we had somebody make like a forged painting or something like that, or an artifact, and they claim it's old, but it's full of carbon-14, and there's no way it can possibly be that old, we could use that as a way to tell how old something is. We can also use the same principle to tell the source of materials, like whether something is made from a living plant, because it'll have carbon-14 in it, or if it was made synthetically, where it will be all carbon-12 because it was derived from petroleum products that were buried in the ground. So we can use this in a variety of different ways to get a sense of the origin and how old something might be. So typically when they do carbon dating, they'll use the year 1950 as their reference point. Again, there's been a lot of nuclear bombs gone off since then, a lot of fossil fuels burned since then. So like I say, it may be difficult for future archaeologists to figure out what's been going on in these past 100 years or so, but keeping in mind that we can typically go back quite a good ways. And if we think about this as a first order decay process, right? So radioactive isotopes, it matters. So if I start with a certain amount, like if I start with, say, 500 atoms that are radioactive, after one half-life, approximately half of them will have decayed. And then after another half-life, approximately half of that half that are still around will decay. So this process over time is a continual halving until there's essentially not many left. Usually after 4 or 5 half-lives, there's not a whole lot left of anything that undergoes a radioactive decay process. So we use the half-life, which is, like I said, about 6,000 years, to get a sense. So anything too much more than, 3 or 4, maybe at most 5 of these, it's going to be hard to date because there's not going to be any carbon-14 left. So we're not going to be able to date like dinosaur bones or anything like that with carbon dating. It's just not going to work. There's no carbon-14 left. And like I say, there's a halving process that's taking place. And I've got a little more information I pulled from chapter 12, which we'll go over in the next unit that won't be part of this test. But I pulled some of that into here to help us get a sense of what exactly is going on and how these half-life calculations work, because the text makes some assumptions that we did these in a different order than how we're going to do them in. So let's take a look at that, and which is going to come up here. But first, they got another example here. Oh, because I mentioned the dinosaur bones. How would we date things that are so much older than what carbon dating can handle? Another key dating system is potassium-argon dating, which can be used to date things that are millions and billions of years old, because they have much, much, much longer half-lives. So that system can be used to get us a sense of how old other things are, like the age of the Earth or dinosaur bones or things like that. Okay, so we've got an example in the text of using radiocarbon dating, and like I say, we're going to look through some chapter 12 stuff to help us get a sense. They use the example of the Shroud of Turin, right? People have said the Shroud of Turin should go back thousands of years, and other people have said that it's a medieval forgery, right? So carbon dating might be able to help us, because it could distinguish something that's maybe only 600-700 years old from something that's maybe 2,000 years old. That's a big enough time difference, and that's far enough in the past that this could give us a really good sense of what's going on. So before we consider that, let's again look at the concept of a half-life and how this works, right? So if you've taken a calculus class, you may have a greater familiarity with things like logs. I'm going to assume that you don't have a whole lot of that, so I'm going to use these equations just sort of as they are and teach them as they are, because I'm going to leave that to a math class. But if you do understand it, and if this kind of brings that back up into your mind, be aware that, yes, the derivation of some of these equations and processes do come out of the integration that they mentioned here is a calculus-derived integration. So we've got a natural log here. So again, that's the ln. That's not the log base 10. That's the log with the e, with the Euler constant. So remember which one they are here. So this equation tells us we can calculate the half-life using the integrated rate law. So we've got an amount of material starting at some time t, and then we've got an amount that's there originally at some time 0. So time t is some distance in time from some time 0. So if it's 5 minutes, it's 5 minutes, and then t is 5 minutes. You can choose your time unit as you want. You just want to make sure that everything is all in the same time unit. Your choice of it should depend on what you're provided in terms of the half-life, because we're going to use the half-life to get the rate constant K, which is the other thing we might be missing, right? If we were going to use a problem like this, we might know how much time has passed and how much we started with, but we want to know how much is left. Or any of those three variables, we might know two of them but need the other one, right? So what we're going to want to be able to do is get K. So it turns out that as long as the process is what's called first order, which is what all nuclear decay processes are, then there's a specific relationship between K and the half-life. So if we plug in 1/2, we can now derive that. If we know the length of a half-life, we can derive the value of K, because now we have the left side of the equation, and if we know the half-life on the right side, we can get K. So let's take a look at this a little further here. So the half-life of a first order process is equal to the natural log of 2 over K. Or you could rearrange this and say, that natural log of 2 over the half-life is equal. You can solve for K in this if that's also what you need. So bear in mind, these are some of the equations that we'll need in our arsenal point. 693 is just a rounding of the natural log of 2. And as we can see in this example, again pulled from chapter 12, we have this continual halving some arbitrary time and over 4 half-lives. We can see that we start with a certain amount at time 0. It gets halved at t1/2 at the half-life, and then at the second half-life, or the fourth life, you can think of it that way, now it's down to 1/4 of what was there. Then the next down to 8, an eighth after the third half-life, so each one is a halving, each successive halving. So it never eventually reaches 0, but it gets close enough that in real life that it essentially is all gone. So we can also use this relationship to come up with a decay rate, a process of how long this decay takes, because a lot of times in these example problems, they'll tell you what the rate is, the decay rate, and we can use that decay rate to also relate to the same K that we saw before in a previous equation. So if we know what that is, we can get N, the number of nuclei, times some rate. So this is also going to be helpful to us in solving this particular question. So we can also perform an integration on that process and come back to the original equation that we were looking at the beginning. And again, we can see the relationship between the half-life and the decay constants as I discussed. So these equations that are in boxes, you should write these down because they're going to be very important for how to solve these nuclear decay problems. And I'll have one of them on an exam, and you may see some of them on a homework. We're going to work through this Schrader-Turing example after we go through it. And I put this in a box here, this one here. Again, you want to make special note of this particular equation, because if you know the half-life, t1/2, from the problem, and you know the starting amount and some time, t, you can use this to calculate what's left at a particular time. Or if you know any of the other ones. So this is now sort of the resolved version of what we looked at the beginning, where all you need to know coming in is the half-life and 2 of these other 3 variables, and you'll be able to solve this equation. So this is a key one to write down because it's going to be key to solving pretty much all of the nuclear decay problems, and it'll also work in first order processes, which we'll see in chapter 12 when we examine rate laws. So continuing on with the original Schrader-Turing problem, we've got a solution. So we've got some ratio t, that n at some time. The capital N is just the amount of stuff. Typically it's in number of particles, but it could be in anything that's proportional to the number of particles. So we could theoretically do it in grams. It'll all calculate out. And then we have N0, which is our starting amount. So they say here, to date the shroud, we need to calculate the time that corresponds to the observed decay rate. So they put in a decay rate, which was provided in the problem, the 2 rates. They said that the original rate, and they got another rate, and they plugged those in. And then we can solve this using the half-life of carbon-14, which is 5,715 years. They put in the natural log of 2, and they're able to solve this to 615 years. So again, they use the reference of 571, or they try to date it to a precise date, but carbon dating is not, because of various factors, like I mentioned, volcanoes and things like that. It's usually good for a rough approximation of a particular era in time when things are from. Is it exactly 615 years? Probably not. But this definitely shows it can't be 2,000 years old, right? I mean, it could be, somewhere in the range of 550 to 650 kind of years. It's somewhere in that 50 to 100 years sometimes with these. Sometimes, depending on the artifact and the exact time frame it's from, the carbon dating can be a little better, but it's usually like a 20-year span, kind of like at best. It's usually 100 years to about 20 years in the range that we're talking about. But still, this puts this in about a medieval origin period. This would show that it's not 2,000 years old. Okay. So briefly before we go, because that's our last topic here, we're going to talk a little bit about naturally occurring nuclear reactors. So what's kind of interesting is that it is actually possible for nuclear reactors to form naturally if for some reason there was enough available radioactive isotopes somewhere on the planet, right? And in the core of the Earth and in the mantle of the Earth, there are nuclear processes going on that are keeping the Earth molten. So there are nuclear processes that are still happening there, but that's typically when people are thinking about some kind of natural reactor, they're thinking about something on the surface, right? So at one point, many billions of years ago, there was actually enough uranium in an enriched enough state that we could actually have a spontaneous self-sustaining chain reaction. And they found this at this mine site in Gabon, Africa, near some diamond or gold mines when they were digging down there. They call these fossil reactors. And it's really interesting that that's possible, right? We typically think of this as having to be something constructed or something set up, but finding nuclear processes occurring in nature, like I say, other than like in the core of a planet or something like that is very fascinating. And they say these differences closely resemble those found in spent fuel from modern nuclear reactors. So how did we find out that this happened? Because we found the products of this process, and we were able to show that those were very similar to those that we would find in a modern nuclear reactor. So somewhere about 2 billion years ago, there was enough uranium still around on the Earth in some of these minerals that this could happen without artificial enrichment. And so they mention a little quickly here, why doesn't this happen today? Again, that's because there's not enough visible uranium left on the planet in an enriched enough state that this would be able to happen on its own. But it's interesting that they talk about how these reactors would cycle on and off for a couple of hours, and they'd create extreme heat, and they'd boil away all the groundwater in a space, and they would form different kinds of minerals and different processes that you wouldn't typically see outside of these extremely high temperatures. So again, this is just something to note, and I'll have a quick bonus question just about whether or not it's possible, why it can't happen today, and what element keeps this going, like that it's uranium that is naturally occurring that keeps this process going. Okay, well, that's about it. That's wrapping up for this Chapter 22 presentation. Thank you very much for listening and being with me here today, and let me know if you have any other questions. Take care and have a good evening.